Once grave was here.
I am the Moor who has awoken thee.
Whoa, no way, it's the Moivre!
I hate this man. He tortured us with math concepts.
You know me from math? Does that mean you know my theorems?
Wait, I think I remember we learned this in math class.
Well, normally I have to kill you for defying my grave. But if you know my theorem, I'll let you live.
Sure. So, Euler proved that cosine theta plus I sine theta is equals to e to the I theta. That means that if we raise this entire expression to the nth power, we can see that it means that e to the I n theta is equal to cosine n theta plus I sine n theta. That means that the Moivre theorem is proven.
Who the hell is Euler? Sound like a filthy Protestant, not a true Frenchman.
Well, if you don't like Euler, you can always do it by the principle of mathematical induction. Here, I have some paper, let me show you.
This is a very straightforward proof by induction. Induction is a method to prove that something is true for all elements in an infinite set, in our case, for all positive integers n. It works by proving that it is true for a base case, or the smallest number in the set, so in our case that would be 1. And after that we can prove that each element follows from its previous element. With this logic, we can prove that a statement is true for each element by repeatedly applying the inductive step. In our case, we will take cos theta plus I sine theta to the k plus 1th power, and after expanding the brackets, we could use the idea that I squared is minus 1 to group our terms into real and imaginary. By using trigonometric identities, we can verify that cos theta plus I sine theta to the k plus 1th power is cosine k plus 1 theta plus sine k plus 1 theta, given that it is true for some integer k. Hence, the statement can be proven by mathematical induction. Furthermore, we can understand this problem by considering the infinite power series expansions of sin x, cos x, and e to the x. As each term is added, the polynomial gets closer to the real function, and with infinite terms, they are identical. Maybe here you can already see the pattern between sin x, cos x, and how they add together to become e to the x. First, we can plug theta into x and times the sine function by I. Similarly, we can plug theta into cos x. Next, we can use the powers of I, where I squared is negative 1, I cubed is negative I, and I to the 4 is 1. We can see that the terms where theta is squared is negative, where theta is cubed is negative and imaginary, and where theta is raised to the 4th power, it is positive. Hence, by taking I to the appropriate power, we can make all our terms positive and group the I and theta together. We can do the same thing to our cos function, and finally, we just need to add the two together. You can see that we can get our original expansion for e to the x, where it is 1 plus x squared over 2 factorial plus x cubed over 2 factorial, so on and so forth, where instead of x, we have theta. Looking at our trigonometric functions in this exponential form can give us a new perspective on our familiar trigonometric identities. Either by constructing a big triangle in a square or a circle, we can technically use geometry to prove this identity, but here we can see that using e to the I theta is super simple and straightforward. We can further define each individual function sin x and cos x as a combination of exponential expressions. Using the fact that cos of negative x is the same as cos x, we can use the difference in sum of e to the I theta and e to the minus I theta to write sin x and cos x, both real functions, as a new function using complex numbers. Cos x and sin x are fundamentally functions used to parameterize the equation of a circle. The trigonometric identity cos squared x plus sin squared x equals 1 is linked to the equation of a circle, x squared plus y squared equals 1. This means that every point on a circle is represented by two coordinates, cos x and sin x. Similarly, cos x and sin x are functions used to parameterize the equation of a hyperbola. Each point on the hyperbola can be represented by the coordinates cos x, sin x, and since the equation for a unit hyperbola is x squared minus y squared equals 1, the equivalent identity for our new hyperbolic functions is cos squared x minus sin squared x equals 1. The hyperbolic functions are very much connected to our familiar trigonometric functions. And we can see that when we write each of them in their exponential form. We can see that simply by multiplying by I, we can switch between the two, hence why they share so many properties and identities.
Whoa, you guys really touched my heart. You not only made my day, but also my life. I can now rest in peace, knowing my contribution to mathematics is both completed and remembered.
Rest in peace, the Moivre.